It is 1:45 a.m. on the morning after the HSC 2025 chemistry exam, and I've just finished going through the paper. I've got lots to talk on it, and the solutions are coming in the video just after this. To summarize my impression of the 2025 HSC exam, it was an easy exam. There's no two ways about it. This exam will go down as probably one of the easiest, if not the easiest, HSC chemistry exam I've ever seen, and that's coming off the back of 2023 and 2024, which were also easy exams. The big question everyone asks is, what do you need for a band 6? I genuinely think it's going to be 89, if not 90, to get a band 6 for this exam. The scaling will not be generous at all. If you're lucky, you'll get scaled up 1 towards the high end, and then if you're down towards the 80s, you might get maybe 2 or 3 70s, a few more than that. But really easy exam. It genuinely only had maybe one curveball short answer question, question 32, and for the multiple choice, only one multiple choice stood out to me as a difficult one, and I'd say that was question 19. But apart from that, everything else is pretty much regulation. If you'd done your work, if you'd been a Catalyst student in particular, this exam would have been a breeze. And I don't think you had any excuse if you'd done the work to get the dream mark that you were hoping for. And if you didn't, then I guess it's unfortunate, but it's always the case with these easy exams where it has to be perfect on the day. And it's frustrating, it really is, but that's all I really have to say around this exam. I'll get straight into the solutions. If you haven't met me before, my name's Jeff, and I'm the founder and head of Chem at Catalyst. We basically run a program that pushes you 3 to 5 weeks ahead of class pace through the year. We run a HSC exam intensive program at the very end of the year for the HSC itself, and through the program, we help our students achieve band 6s, 99 plus ATARs, and dream marks across the board, even if that's not exactly what you're aiming for, those super high marks. We'll support you on your journey. We give you a super welcoming environment to learn chem and actually learn to love the subject. I think that's the most important thing. But without any further ado, let's get into this paper. 2025 HSC exam, work solutions, here we go. All right, so let's get straight into the multiple choice. 20 multiple choice questions as always. The first question is an aqueous solution of an unknown acid HA is represented below. You're given 2 H plus and 2 A minus ions. Which row of the table best describes the solution? This is showing us a strong acid as all of the acid molecules are dissociated, and it's not particularly concentrated with only 2 acid ions or 2 acid molecules dissociated respectively. So this is going to be a non-concentrated solution, giving us B for question 1. Question 2, which reaction type is shown? We have a butane 1-ol molecule being reacted into a butanone. This is a oxidation. It would not be addition, reduction, or substitution. Question 3, which of the following structural formulae represents 1,2-dibromopentane? All of these are pentane chains, so we're simply looking at where the locant of 1,2 describes the bromine to be, and this lines up with option A, where we have a bromine on carbons 1 and 2. The other options do not make sense. Question 4, a student is presented with 2 clear color solutions. One contains lead and the other sodium ions. Which ion can be added to the solutions to identify the solutions? The best answer here is going to be iodine. When you add iodine to lead, this will form a lead iodide precipitate. It will not precipitate with sodium, as you can distinguish them. Ammonium will precipitate with neither, nitrate with neither, and acetate with neither. Question 5, PCl3 and Cl2 were introduced into an empty sealed vessel. PCl3 reacted with Cl2 to produce PCl5. PCl3 gas and Cl2 gas turn into PCl5. Which graph best represents the changing concentration of Cl2 as the system approaches the equilibrium point? So we're starting with PCl3 and Cl2 in our reaction chamber, which means that we start with a non-zero Cl2 concentration, which instantly rules out B and D, which start with a concentration at 0. Out of A and C, we know that as equilibrium is approached, the rate at which concentration would decrease with the reactant is going to become slower and slower. Hence, you have a flatter and flatter gradient until you approach constant concentration, which represents equal rates of forward and reverse reaction. So C is correct. A would represent a linear reaction going to completion. Doesn't quite fit what we have here. Question 6. What is the pH of a 0.25 mole per liter solution of HCl? We know that HCl is a strong acid, so this 0.25 mole per liter concentration is going to be our concentration of H+. pH is equal to negative log of H+ concentration, which is equal to negative log of 0.25, which comes to putting the calculator, negative log 0.25 comes to 0.60 to 2 decimal places, which lines up with option D. Question 7, copper ions can form colored complexes with water molecules and with chloride ions in dilute aqueous solutions. Out of the following, which analytical techniques would be most suitable to distinguish between these two complexes? So this one actually is a little bit trickier. We can rule out carbon NMR straight away because there's no carbon present. We can also rule out atomic absorption spectroscopy since both of the complexes have copper, and there'll be no observable difference between the two. This leaves us with UV-Vis spectrophotometry and infrared spectrophotometry. UV-Vis is better in this scenario as we're talking about colored complexes, which are going to have distinct absorbances across the wavelength spectra of the UV and visible range. So when you generate those two curves, you would be able to see that one curve would have its own distinct pattern, whilst the other would have its own distinct pattern at certain wavelengths as well. And looking at the peak wavelengths, the one that absorbs orange light better and the one that absorbs red light better, dipping into our colorimetry theory a little bit, would be able to distinguish between the two. And if we have data where we can compare the spectra that we get from this process, we have data to compare against, we can instantly identify the complexes as well. So C would be best. The reason why A doesn't work is because the bond vibrations in the complex ligand to metal ion bonds would be quite similar in their vibration energy levels that they need to jump. And so there's not significant difference between the two molecules, even though there is a H2O, which some people might think, hang on, is there an OH representing a broad trough around either 2,500 to 3,000 or the carboxylic acid OH? This isn't bonded to a carbon. And so you're not going to see that same trough that you would in, for example, a carb acid or an alcohol. So A doesn't quite work. C is the best answer for question 7. Question 8, an alkene with X with only one carbon-to-carbon bond undergoes an addition reaction with an unknown substance to produce Y. X plus the unknown substance goes to Y, and we're given the two mass per charge ratios for X and Y. Which of the following can be the unknown substance? So we know whatever the unknown substance is accounting for a change of 20 atomic mass units between whatever X and Y is. So X, when combined with this other substance, suddenly will have a mass relative to charge ratio, which is 20 units higher. And so we need to go and look at each of these substances and look at their particular atomic masses. So water is going to have an atomic mass of about 18, given that it is H2O, 2 hydrogens, 1 each, and an oxygen. Fluorine, checking our periodic table, fluorine is going to be F2, which means you have 19 plus 19, as it is diatomic, and that is of course going to be too big. Ruling that out as well. Hydrogen is 1 plus 1, which is too small, and hydrogen fluoride is 1 plus 19, giving us the perfect 28 is going to be D. Question 9, some Torres Strait Islander peoples pound the leaves of the vine Derris uliginosa to extract a chemical called saponin. Saponin is a relatively large molecule that contains both a water-soluble carbohydrate chain and a fat-soluble side chain. Which of the following is the most likely use of a saponin? So given that we have a water-soluble portion and a fat-soluble portion, we're instantly thinking this sounds a bit like what we know about our soaps and detergents, where we have a hydrophobic or lipophilic and hydrophilic end. And what is being described here is therefore an emulsifying agent. And A lines up closest with this. Neutralizer insect bites is implying an acid or base, and doesn't quite line up here. As a dye for pigmentation and painting, again, not really. It's not really describing a colored property in the stem. and D as an additive to food for flavoring and tenderizing. We don't have any indication that's what it's used for here based on the properties they give. So A is the best option for everything here, forming the bridge between water and fat-soluble grease, or fat, grease, or oil that might be used to clean. Question 10, which of the following options lists all the forces that represent... Question 10, which of the following options lists all the forces that are present between molecules of butanoic acid? It's between molecules, so we're talking intermolecular force. This means that we can rule out covalent bonding in both of these options. That's intramolecular. And we know that butanoic acid is a hydrogen bond forming molecule. So drawing out quickly the carboxylic acid, we know that it is able to form hydrogen bonds between its lone pairs and its polarized hydrogen. So this can go off and form hydrogen bonds with another carb acid. And they'll typically form dimers. I won't draw it in this case, but this is what you would expect to see. So this H bond can exist, and all molecules that form H bonds can also form dipole-dipole and hydrogen bonding. So D is best, B is not great, nor is A and nor is C. Continuing on, question 11 shows us two substances X and Y. X is a carboxylate anion, Y is an amine. Which row of the table correctly classifies these substances as Bronsted-Lowry acid or Bronsted-Lowry base? So we know carboxylate is the conjugate base of a carboxylic acid, meaning it will have basic properties and the ability to accept protons. So X is a base by Bronsted-Lowry theory, and Y is an amine, also a base that we commonly recognize, accepts protons, does not donate protons. So we actually have two Bronsted-Lowry bases here, both X and Y. Neither is an acid. Option A is correct. Question 12, consider the following reaction. What is the correct equilibrium expression for this reaction? Immediately we see we have a solid. We exclude solids from our equilibrium expressions. So writing this out, it's going to be iron nitrate concentration divided by silver nitrate concentration cubed, keeping the products on the bottom, the reactants on the bottom. And we would line this up correctly with option B. Question 13, which row of the table correctly shows the expected signs of the enthalpy, delta H, and entropy changes for the complete combustion of octane above 100 degrees Celsius? Combustion is one of our famous case studies. We know that it is a vastly exothermic process, and because we are turning a large molecule into lots of smaller constituent water and carbon dioxide molecules in combustion, even though we are consuming some oxygen, we end up with far more moles of gaseous substances at this high temperature of 100 degrees Celsius. And so this is going to be a entropy positive change where we are becoming more disordered. And so 13, the answer would be C. Question 14 gives us an equation for hydrogen iodide and how it dissociates. We're given its delta H. The equilibrium expression formed during this reaction was investigated in two experiments carried out at different temperatures. The initial and equilibrium concentrations for both experiments are shown in the table, with only the KEQ for experiment 1 shown. Which row in the table correctly compares the features of the two experiments? So first of all, we have to compare the KEQ. So to calculate this, we need to write out what it would appear like in our expression. So it would be 0.02 times 0.02 divided by 0.04 squared. And when we put this in our calculator, we get out 0.25. This is our K in experiment 2. So we can immediately see our KEQ is bigger in 2, or in other words, lower in 1. So we can rule out C and D. The temperature of the experiment, given that the delta H is positive, the more that proceeds, the lower the temperature will become. And we see that in the initial concentrations of experiment 1, we see that, let's just take one comparison. Iodine concentration goes up by 1, so it's preceded by 0.01 moles per liter, whereas experiment 2, 0.04, goes down to 0.02. They're actually proceeding in opposite directions. So we have to consider which is the exothermic direction, because that one would result in a higher temperature. We know that the reverse reaction is the exothermic direction. So looking at this, we can see that because experiment 2 is proceeding in the reverse direction, this would result in a higher temperature, whilst experiment 1 would result in a lower temperature, and we would therefore say it is higher in 2 for question 14. Question 15 asks us to consider a sequence of reactions, and looking at the reactions, we react prop-2-ene-1-ol with H2, which means we do a hydrogenation, giving us prop and 1-ol, getting rid of the double bond. We do an oxidation of this primary alcohol, giving us now a propanoic acid as follows. And finally, we react with methanol and an acidic condition, implying this is a esterification. And this would now give us methyl propanoate. So matching up the structures, X is going to be one of these three. Y is going to be one of this, or this. And Z is going to be our ester, giving us option D for 15. Question 16, a single straight strand of polyester was produced through a condensation reaction of 1,000 molecules of 3-hydroxypropanoic acid. What is the approximate molar mass of the strand in grams per mole? So we have to consider the implication of how many H2Os are lost. And we should know that when we make a polymer, that every single monomer reacted minus 1 is the number of waters lost. So if we react 1,000 molecules, given that this is the only monomer, we see the OH and the carboxylic acid on the other end, we are going to have 999 H2O molecules lost, which is going to account for this difference in 18 between the answers. So let's look at what the molar mass is going to be. For 3-hydroxypropanoic acid, we can count up that we have 1, 2, 3 carbons. We have 1, 2, 3 oxygens. And we have 1, 2, 3, 4, 5, 6 hydrogens. Adding that all up is going to be the molar mass being equal to 3 times 12.01 plus 3 times 16.00 plus 6 times 1.008 being equal to, let's add it up, 3, 12.01 plus 3 times 16 plus 6 times 1.008 gives us 90.078 grams per mole. Okay, so given we know what the molar mass is and we do 1,000 molecules worth of this, the molar mass of the polymer is going to be equal to 90.078 times by 1,000, and we have to factor in the waters that we lose. So we take away the molar mass of water, 18.016 times by 999, one less than number of monomers. And that is going to give you times 1,000 minus 18.016 times 999. This gives you 72080 grams per mole, giving us B as the best option. Be careful with the water in these polymer questions. 17. The chemical environment of an atom depends on the species surrounding that atom within a molecule. In which of the following compounds does the number of carbon chemical environments equal the number of proton chemical environments? So, going through one by one, this first molecule has one carbon environment and a second carbon environment which is unique. We can also see that we have all of these hydrogen environments in the same environment because they're all in the same carbon environment. And finally, we have a unique hydrogen environment down here. So we actually do have 2 carbon environments and 2 hydrogen environments. I will turn off the notifications. And that actually gives us the correct answer. 17 is A. We can check the other options. So with B, we have 1, 2, and 3 H environments, and we have only 1, 2 carbon environments. Doesn't quite work out. So 3 versus 2 doesn't work. C, this is 1, this is 1. That's the only carbon environment, and then we have 1, 2 different carbons. So 1, well, I should do 2 and 1, keeping it consistent, and the other one should be, say, 2 and 3. And finally, with option D, we have 1, 2 hydrogen environments. These are different. I should do a different color. Different. And then the carbons, we have 1, 2, 3. These are all unique environments because they're not bonded to exactly the same things. Ruling out D, since we have a 3 versus 2 situation. So A is correct for 17. Question 18. The concentration of silver ions in a solution is determined by titrating with aqueous sodium chloride. Using yellow potassium chromate as an indicator, which row of the table correctly identifies the color change at the endpoint and the more soluble salt? So I've actually gone ahead and inserted a diagram. This is the famous Moore's method from the start of Module 8, your precipitation titrations. This is a case study, and as I always told catalyst students, the case studies are accessible. This is exactly why you prepare them for a question like this, because there's no context about the KSP of chromate. You can't figure it out in the exam room. You have to know the case study. So what happens here? In Moore's method, for those who don't know it well, you have silver ions in a burette being let down into a conical flask containing chloride, which will form precipitate as you go along. However, you also have another ion in there, chromate, and silver chromate eventually will also form precipitate. The question is which forms first, and silver chloride will actually be the precipitate that begins to form initially first. So as you let down your silver, this starts to form a pale precipitate with the silver chloride, and reacting until all of it has been precipitated. Then the next bit of silver you place in, so I'll notate it in green now, so you've done all of your chloride out. The next bit of silver is then going to go seek out the chromate, which turns it into a red precipitate, silver chromate, and eventually that becomes perceivable by the eye. That is your endpoint. Weakness of this titration method is you end up with titration error, but for the context of this question, we just need to know what happens in terms of what's more soluble and what color change we see. We should see a change from yellow to red. And the more soluble salt out of silver chloride and silver chromate is silver chromate, since it forms as the second precipitate. This concept actually comes back later in the exam as an important one in terms of what precipitates first. So stay tuned for that. But the answer is B. Question 19 asks us where we have 0.1 moles of sodium acetate dissolved in 500 mils of 0.1 mole per liter HCl in a beaker. The solution has a pH of 4.8. 500 mils of distilled water is added to the beaker. What is the pH of the final solution? So the trap with this question is it seems like it's just a simple dilution where you can, double the volume, halve the moles of H+, and then find the diluted pH. But what you may not see is that this is actually a buffer. So we have sodium acetate being added into HCl. So you have a conjugate base, and the HCl is a supply of H+. What will then happen is you have a reaction between the acetate, so CH3COO- plus H3O plus supplied by the HCl, forming an equilibrium to make CH3COOH plus H2O. So it is a buffer system where you would essentially have 0.1 moles of sodium acetate. You're going to have 0.05 moles of HCl, since 0.5 liters times 0.1 is equal to that. And once all the HCl, H plus or H3O plus from the HCl is reacted with acetate, you're left with 0.1 minus 0.05 acetate, since that would excuse me, that would leave you with just 0.05 moles. And for the acetic acid, you would have formed 0.05 in the reaction process, leaving you with 0.05 moles as well. You'll then notice that the moles or the concentration of acetate is equal to that of acetic acid, and when this is true, you end up forming a buffer, and you can show that pH is equal to pKa, since the log in Henderson-Hasselbalch formula, if we wanted to probably prove this, the log of concentration of A minus divided by HA, Henderson-Hasselbalch, because our A minus and HA concentration are the same, this would be equal to saying pKa plus log of 1, or in other words, is equal to pKa. So we know that our pKa for this reaction is equal to 4.8. Now, that is helpful. We can then go on and solve the rest of this question either using a Henderson-Hasselbalch or using an icebox. So I'm just going to show the Henderson-Hasselbalch way in this context, so it's easier for multiple choice. But if you were to dilute all the concentrations by a factor of 2, since we're adding an equal volume, your new Henderson-Hasselbalch formula is going to be equal to pH equal to pKa 4.8 plus log of A minus, which is now going to be diluted down to 0.05, because the initial concentration would be 0.1 molar and 0.1 molar, if I was to find those from the 500 mils initially. The new concentration will be half, so 0.05 on 0.05, which again gives you the same trivial expression of pH is equal to 4.8 because of this buffer system. The correct answer for 19 will be C, not D, which is the commonly mistaken option here. So for question 20, the solubility constant for silver oxalate was determined using the following method. 2 grams of solid silver oxalate was added to 100 mils of distilled water. A sample of the saturated solution above the undissolved silver oxalate was diluted by a factor of 2,000 times using distilled water, and the diluted solution was analyzed using AAS, and the calibration curve is provided below. The absorbance for the diluted sample was found to be 0.055. The question asks, what is the KSP? So we know that, reading from the graph, as I've drawn on already, that we have a 0.11 mole per liter concentration of silver in the diluted by 2,000 times solution, and that's times 10 to the negative 6. So the concentration of silver in the undiluted sample is going to be equal to 0.11 times 10 to the negative 6 times 2,000 to reverse that dilution. And that is going to give us 0.11 times 10 to the negative 6 times 2,000 gives us 0.00022 molar. The concentration of oxalate, C2O42 minus, is actually going to be equal to half of that, since it forms in a 2-to-1 ratio with silver, so silver being 2, oxalate being 1. The concentration is therefore 0.00011 molar, and the KSP is equal to 0.00022 squared times by 0.00011, giving us 5.324 times 10 to the negative 12. This is equal to option B. And that's the end of the multiple choice. So I think overall, the impressions of multiple choice. There's probably, out of all the questions, I wouldn't say really anything that's out of the reason. Questions 1 through 10 are all very regulation. I guess the only tricky one may be question 7. You might have been tripped up on the IR versus UV vis. 8 was fine. 9, if you recognize it was soap or a emulsifying agent, very straightforward. All these were fine. 14 was fine. 15 was fine. 16 could have caught you out if you haven't seen these condensation polymerization questions with water being removed. But regulation, if you've seen it. Carbon environments, hydrogen environments, regulation. I would say that Moore's method is also regulation. You should have come across and you should know this procedure. I think question 19 is probably the hardest question in multiple choice. If you didn't see the buffer and you don't really know what's going on with Henderson-Hasselbalch, you can't prove it for sure. If you recognize there's a buffer and you know it's going to resist the change, you can make the deduction it's probably not going to change in pH by very much. And so you're probably going to stay at about 4.8. But it was an easy trap to fall into, go for the 5.1. And 19, I'd say, is the hardest question, multiple choice. Question 20, I would say, is regulation, even though it's dressed up as a bit of a longer question. Really, once you understand what they're getting at with the dilution, it's not too bad at all. So overall, my impression, pretty straightforward multiple choice. Very 20able, at least 19 or 18able in my opinion. And that's pretty much all. Let's move on to short answer. Hey, just jumping in quickly in the middle of this walkthrough. If you're enjoying this so far, it would go a long, long way if you could hit the subscribe button and the like button on just down below. It doesn't really cost you anything. It would help us out immensely and we'd really appreciate it. So that's all I have to say. If you're enjoying it, keep watching. Short answer coming right up. All right, so let's get stuck into these short answers. First up is question 21, straightforward question. Reaction is a substitution of halogen with a bromine onto an alkane, so butane. The reaction condition is going to be UV light in order to make this proceed, and the IUPAC name of the product that is shown is 2-bromobutane. You need the punctuation to be correct. Question 22. Outline why quantitative and qualitative analyses are both important in determining water quality. So you have to talk about the two terms, quantitative and qualitative. They are different. Qualitative analysis is important for assessing the types of contaminants present in water, and this is just a suggested answer, as are all of these answers. The mark allocation is not exactly clear yet, but this is just what we think it'd go to. So it would make sense. There's one mark for qualitative, which is what is spoken about first. So to identify the types of contaminants, giving an example as in this response. So maybe we're looking for red color indicating iron oxide, or an algal bloom may indicate phosphorus contamination. Those are qualitative signs. Quantitative signs are helpful for assessing the concentration of different contaminants and assessing just how severe the contamination is, and also guiding how severe an intervention is required as well to remove that contamination. You don't have to say everything here. This is just what we thought would make this response complete. So 2 marks for question 22. Question 23. A student attempted to determine the percent weight for weight of the sulfate in a sample of solid fertilizer. They use the procedure described below. Steps are all shown below, where you weigh a clean dry beaker, add fertilizer to the beaker and weigh again, add 250 ml of distilled water and stir thoroughly, add 20 ml of 0.1 mol per liter barium chloride solution, filter out the barium sulfate precipitate using distilled water to ensure all the solids transferred from beaker to filter paper. You're then putting the filter paper and precipitate onto a weighed watch glass and letting it dry in the sun, weighing the watch glass, the filter paper and the precipitate, and then calculating percent weight per weight. Fine. So the question asks you to justify 2 changes that can be made to the procedure to ensure more accurate results. Now we've given you 3, but you only have to say 2, and of course justifying it for the 3rd mark. So in my mind, it's probably going to be 1 mark each for each change that you would make, and then the 3rd mark goes to have you justified both. It could also be 1 mark for each identified and then 1 mark for each justification too, but either way you have to justify. So what you could have suggested is, number 1 and most obvious, I think, is using a desiccator oven in order to dry your sample further rather than just 20 minutes of sun drying, which is probably going to leave water behind. If you use a desiccator oven, this will lower and move the experimental weight per weight closer to the true value, since you are removing that excess water, getting a truer measurement of your mass. 2 other options you could do. Secondly, you could do washing with different electrolyte solutions, washing that fertilizer in different electrolyte solutions in order to eliminate other potential ions that may also react with the barium. So this might be carbonate ions. Barium carbonate is less soluble than barium sulfate. So it may be helpful to precipitate out the carbonate first, or react it off with an acid or something similar, in order to prevent excess mass being produced that isn't actually sulfate. So that would help you, again, bring down the percent weight per weight closer to the value. And finally, instead of using barium chloride, it might be better to use, for example, barium nitrate to prevent precipitation of chloride with other potential ions in solution, such as silver. So some suggested answers here. Once again, question 3, nothing too crazy here. Question 24 is a limiting reagent question with a little bit of organic organic drawing and molecular geometry to start off. So the 65 grams of ethane gas react with an excess of gaseous hydrogen chloride to produce chloroethene. The structural formula of ethine is going to be as shown on the screen, making sure you have a triple bond between the two carbons and one hydrogen on each to obey the octet rule. The shape of this molecule is linear. Since there are only two bonding groups and no lone pairs on each of the respective carbons, it is a linear shape. Part B asks you then, with the molar masses of the compounds in the reaction being provided, so ethine, hydrogen chloride, chloroethene, calculate the mass of chloroethene produced using the molar mass provided. Now we have the molar masses, and we have to recognize, first of all, this is going to be a limiting reagent reaction where you have 65 grams of ethine gas and an excess of hydrogen chloride. So the ethine is going to be a limiting reagent. Our first step is to write our equation, as we always do, showing the reaction between ethine and hydrogen chloride to make the chloroethene at the very end. All of these substances are gaseous as identified by the question. Then we can find the moles of ethine, taking 65 and dividing by its molar mass given in the table to give us 2.496 moles. Since our HCl is in excess, the C2H2 must be the limiting reagent, as we've established, and that leads us to say that the moles of C2H3Cl is equal to the moles of C2H2, since that is completely reacted, and we end up with a mass of C2H3Cl of moles times molar mass. The moles that we just found before, 2.496 times by the molar mass of chloroethene, 62.5, giving us 156 grams. And the sig figs for this response, since you have used 65 grams, which is 3 sig figs, and all these molar masses are 4, leave to the least sig figs 156 grams. Keeping in mind there is a sig fig question in every HC exam. This could be it. It could be the next calculation. You don't know. So everything, make sure you check your sig figs. Question 25, another calculation is an esterification where you have 0.267 moles of propan-1-ol and 0.298 moles of butanoic acid with a catalyst. You're given the volume of propylbutanate produced, the density, and its molar mass. So the question asks, sorry, I covered it up, have I? Sorry, no, I haven't. The question asks to calculate the percentage yield of the ester. Now, you start off with, again, an equation just to relate your ratios, although typically it's always going to be 1-to-1 in esterification anyway. You know from the limiting reagent being the propan-1-ol, since you only have 0.267 moles of it, the theoretical 100% yield is if all of this limiting reagent reacted, and you would get 0.267 moles of propylbutanoate. Of course, that's not what's going to happen in esterification, since it's an equilibrium reaction, and technically this arrow should be a equilibrium arrow, and we should also acknowledge that we're making water. Now, the only other thing to add on is then we are given how much propylbutanate is formed, 12.2 mils, and we can convert that into a mass. So 12.2 mils times by the density of 0.873 tells you what mass of propylbutanoate is formed. And dividing by the molar mass, this allows us to find the moles of propylbutanoate formed. And finally, we can find the percent yield, so the actual moles of propylbutanate formed, divided by the total that we could potentially form, 0.0818, so on, divided by 0.267 gives us 30.6%. Once again, checking our sig figs, we have 3, 3, 3, 3, 4. Least sig figs is 3 that we use in our question, and 30.6% is our percentage yield. Question 26 says a hydrogen atom on the methyl group of ethanoic acid can be replaced with a single halogen atom. A general formula for these haloethanoic acids is shown. XCH2COH and X can be either fluoride or fluorine, chlorine, bromine, or iodine. The pKa values of the 4 haloethanoic acids are given in the table, and they're provided in the table as shown there. You are asked to plot these on a graph, and the first big question from the exam is, should this have been a line or a bar graph? And you can see what we think the answer should be. It should be a bar graph. This data is categorical. This is not a continuous variable, so you should not be comparing these through a line trend. It's particularly not a line of best fit. There should not have been a line of best fit anywhere to be seen, no curve of best fit. These should not have been joined up. Now, to get the 3 marks, you need the axes to be correct. So the scale wasn't too challenging, and where you put the F, CL, BR, and I is pretty straightforward as well. A title is advisable, but often not awarded a mark, just something to safeguard your marks. And the bars, of course, had to line up with the relevant measures of 2.6, 2.9, 2.9, and 3.2. So 3 marks there. Part B, describe the trend in the relative strengths of the haloethanoic acids. So as you see, the pKa increases as you go from fluorine towards iodine. The justification, as the halogen increases in atomic number and period number from left to right on x-axis, the related ethanoic acid experiences an increase in pKa. So we're describing the trend. That's the most important thing to do first. Now, this means that you have a decreased Ka, and Ka is proportional to acid strength. So as pKa is equal to negative log of 10 Ka, that's how you justify, so it's inversely proportional. And therefore, the overall trend is that the halogens attached increase in atomic number. The ethanoic acid decreases in relative strength as you go along. You could have also mentioned here electronegativity, but it just asks for a description, doesn't ask for an explanation. So you didn't have to mention a full justification of why this is true. You just had to explain the trend. That's it. Sorry, not explain, describe the trend. And that was it for 2 marks. Question 27. You had mixtures of hydrocarbons that can be obtained from crude oil by the process of fractional distillation. Examples include petrol, diesel, and natural gas. Part A asks you to outline an environmental implication for a use of a named hydrocarbon mixture that is obtained from crude oil. So we could have written for 2 marks that an environmental implication of natural gas occurs during its incomplete combustion. So talking about the natural gas in particular, where highly polluting greenhouse gases such as CO2 and carbon monoxide are released in the atmosphere, as shown in the incomplete combustion of methane. So this is one example of an incomplete combustion equation. You could have also shown it just with carbon monoxide on its own, or CO2 to show complete combustion on its own to also show you're making greenhouse gas. But I think the more pertinent feature is the carbon monoxide. So you could have also written this equation just with the carbon monoxide and balanced it to reflect that as well. Cool. This, of course, again, is not the only thing you could have said, just one thing you could say. Part B, ethene is a simple hydrocarbon obtained from crude oil. Using structural formulae, write the chemical equation for the conversion of ethene to ethanol, including any necessary reagents. Now, all you had to do was do exactly that. Write the structural formulae, ethene to ethanol, draw those two out. You know that this is going to be a hydration reaction, so you need a water molecule. Advisable to show the bonds since we're asked for structural formulae. You may lose marks if you did H2O. That could be where you lose marks. Dilute sulfuric acid. You can also do H2SO4AQ, but it's not as convincing as saying the word dilute. Of course, in an exam situation, just write out the full word to be safe. But otherwise, 3 marks shouldn't be too problematic. States shouldn't be required for structural formulae. Generally should not be required. And now part C, probably the easiest 3 marks you'll pick up in a HSC exam. Draw 2 lines, get 3 marks. When ethanol is reacted with ethanediolic acid, ethyl ethanoate is formed. As shown by the equation, ethanol reacting with ethanoic acid makes ethyl ethanoate and water. The graph below shows a concentration of ethanol from the start of the reaction T0 up to a time T1. At time T1, an additional amount of ethanol is added to the system. Sketch on the graph the changes that occur in the concentration of ethanol between time T1 and when the system reaches new equilibrium before time T2. So we can see that we've established equilibrium by the time of T1 because concentration of ethanol has become constant. At T1, we add ethanol. So there should be a sudden spike upwards as we see here. And afterwards, we have a decrease in concentration at a flattening until it reaches a flattened gradient, telling us we have once again reached equilibrium. Constant concentration means equal rate of forward and reverse reaction in a equilibrium. By T2, this should have been established, and this is our graph. Things that could have cost you marks, if you went below and went beyond your initial change, that would have lost you marks, but there's not really too much you can do wrong here, to be honest. and there wasn't a specified amount you had to go up by, so it could have really been any interval upwards, as long as the resistance was between where you started and where you went up to as the maximum disturbance. All right, question 28, 4 marks. Kevlar and polystyrene are two common polymers. A section of their structure is shown. Kevlar is produced through a reaction of two different monomers, one of which is shown. Draw the missing monomer in the box provided, and the missing box was the one on the left. So this was actually in our Catalyst mock exam 3, written by Sachi. We predicted this exact question, which was crazy. And essentially what happens here is you have Kevlar bonded together, where you have one of the monomers that has a chlorine in it, and you have to take the hint that this is what's been removed in order to be able to bond on the nitrogen in your Kevlar polymer. So essentially what you're drawing out is going to be a benzene with an amine on either side, so a diamine on the benzene, and when this reaction proceeds, this hydrogen and this chlorine are removed in the condensation, making a HCl, and the molecule is effectively joined together there. So this H would go, this Cl will go, you get a HCl condensed off, and then you would get nitrogen bond to the carbon, and that is the polymer. It would propagate on and on with each of these monomers going on. But yes, this would be the expected monomer for part A, predicted by Catalyst in our HSC exam intensive program. Part B, Kevlar chains are hard to pull apart, whereas polystyrene chains are not. With reference to intermolecular forces, explain the difference in the physical properties of the two polymers. Polystyrene chains are composed of nonpolar bonds formed between carbon and hydrogen atoms with a sized Part B. Kevlar chains are hard to pull apart, whereas polystyrene chains are not. With reference to intermolecular forces, explain the difference in physical properties of the two polymers. So, then on to part B, Kevlar chains are hard to pull apart, whereas polystyrene chains are not. With reference to the intermolecular forces, explain the difference in physical properties of these two polymers. So you should be able to look at these two polymers and see that one has highly electronegative nitrogen, one has only carbon and hydrogen. You can immediately tell that one of these molecules is likely polar, and we can confirm Kevlar is polar because it is asymmetrical, or unsymmetrical because it has these carbonyls. The nitrogen it's nowhere near symmetrical. So it's essentially going to be a polar molecule. It's going to have intermolecular forces more than dispersion. So we'll have dipole-dipole because it's a polar molecule. And because we have lone pairs on the nitrogen, lone pairs on the oxygen, I'll just rub this out, has lone pairs on the oxygen, and has a highly polarized hydrogen on every single nitrogen due to the electronegative pull on electrons from the nitrogens inward. This means that we can form hydrogen bonding dipole-dipole dispersion force, significant intermolecular force. Polystyrene, on the other hand, has only carbon and hydrogen bonds, only nonpolar bonds, carbon to carbon, carbon to hydrogen, that is it. So the only intermolecular force in polystyrene is dispersion force. That being said, these bulky benzene rings do bulk up its dispersion force to some extent, making it a little bit harder to pull apart, a little bit more rigid, and both of these I consider to be, I guess, relatively crystalline in their stacking. The model answer is shown here, and it pretty much lays out what I've said, justifying that the reason why polystyrene is harder to pull apart is because of these the reason why polystyrene is easier to pull apart is because it doesn't have as much intermolecular force, it only has dispersion force, and Kevlar has hydrogen bonding, dipole-dipole, dispersion force, all of these, meaning it has much more intermolecular force holding together chains. It's harder to pull apart, and it's extremely rigid. You could also mention the melting point, boiling point if you wanted to explain other physical properties, but the main one they're asking on here is why they're hard to pull apart. So you just had to talk about that. This has kind of gone above and beyond, but this is for 3 marks, part B here. Question 29, consider the following reaction: NO2, N2O4, and delta H is negative 57.2 kilojoules per mole. A sealed reaction vessel of fixed volume contains a mixture of NO2 and N2O4 gases at equilibrium. Explain the impact of addition of argon and inert gas on the temperature of system. This was predicted in Catalyst Mock number 1, and we saw this throughout our Module 5 course repetitively. We rammed it home when we first talked about factors of equilibrium, noting that equilibrium is not affected, the position is not affected by the addition of inert gas if we are considering a reaction vessel of fixed volume. That is the key phrase here. We of course know there's 2 cases of inert gas addition that we can look at, and we've discussed heaps at Catalyst. The other case is your variable volume. So imagine you have a bag, and if you added inert gas into the bag, that increases the total volume, but in doing so, it decreases the partial pressure of all of the gases inside, not just, it would decrease the partial pressure of everything, which means you do have a shift in equilibrium in that case. But this is the fixed volume case. This is the case where you have a box that does not deform. You have a bunch of gas inside already, which have partial pressures, and you can define partial pressure as the pressure of a gas if it was the only gas in the box. Because you're just adding in this extra gas that reacts with nothing, the other gases' pressures, or partial pressures, stay exactly the same. They are unchanged, and partial pressures can be thought of the same as concentration in the context of gas. Because partial pressures don't change, it means you have no shift in equilibrium, and therefore, because we do not proceed forward or backward, there is no change in temperature in the system. It's a trick question. If you had gone to Catalyst, if you had done our program, you would know this. And the answer, model written up here, a constant volume, the equilibrium does not shift upon the addition of inert argon gas. Adding an inert gas to a fixed volume increases the total pressure, as I've been saying, but it does not change the partial pressure or concentration of any of the reactants or products. Since K and Q are based on partial pressures, so you can link it to K and Q, makes it even stronger. And these do not change. K would only change in temperature, Q would change in concentration and volume changes. The system remains at equilibrium. Thus, as the system remains at equilibrium, there'll be no temperature change to the solution due to the sealed reaction vessel being at a fixed volume. 4 marks. I think that sums it up pretty well. And yeah, pretty much all I have to say for 29. Now, question 30. Question 30, phosgene is used in industry as a starting material to synthesize useful polymers. Phosgene, Cl2CO, is a gas at room temperature and is highly toxic. Justify a suitable precaution when using phosgene. So I've told you it's highly toxic. It is a gas at room temperature. That means it will be volatile. It is going to exist as fumes if you use it in your lab, and it's toxic. You can't breathe it in. Therefore, a suitable precaution is a fume hood. I think this is the most obvious one. A fume hood in order to remove any of these toxic fumes from the air, prevent irritation and toxicity. Again, other things you can mention here, but I think this is the most obvious. Part B, phosgene is synthesized by the reaction of carbon monoxide and Cl2 in the gas phase. The reaction is given. Explain why an excess of carbon monoxide and a catalyst are used in the industrial synthesis of phosgene. So, industrial synthesis, we're thinking chemical synthesis, factors that can affect rate, yield, purity, all that good stuff. So, this model answer leads and talks about, with 2 big subheadings, why we would use excess carbon monoxide and why we would use a catalyst. So an excess carbon monoxide and a catalyst are used in industrial synthesis of phosgene to increase yield and the rate of reaction. Good. Big key words. That's what the mark is looking for. Excess carbon monoxide, justification. Adding excess carbon monoxide would increase the yield of phosgene. LCP states that when a system at closed system at dynamic equilibrium experiences a disturbance, it will shift to minimize the effects of the disturbance, and upon addition of excess CO, the system will shift towards the products, going towards the right, to minimize the increase in CO concentration in accordance with LCP, thus increase the yield of phosgene. If you really want to be tricky, you can also mention that because you have more reactants, you'd also technically have a faster rate of reaction, but I think the main point here is the yield. Catalyst. Adding a catalyst will increase the rate of reaction of both forward and reverse reaction, and collision theory states the rate of reaction is directly proportional to the frequency of particle collisions and the success rate of those collisions. Catalyst offers an alternate chemical pathway with a lower activation energy, thus allowing for a greater success rate, increasing rate of reaction. So the 2 arms, you're talking through 2 different important optimizations, yield and rate. That's why it's set up in this way. for 3 marks, they probably want you to talk on 2 different things. And if you talked about rate in excess CO instead of yield and mentioned rate as your catalyst as well, you may get doctor mark for that. But it is not wrong, it's just not the most obvious and strongest response you could have given for the carbon monoxide. It sort of misses the main point. Question 31, 6 marks. Hydrazine is a compound of hydrogen and nitrogen. The complete combustion of 1 liter of gaseous hydrazine requires 3 liters of oxygen, producing 2 liters of nitrogen dioxide gas and 2 liters of water vapor. All volumes are measured at 400 degrees Celsius. Part A asks to use a chemical equation for the combustion of hydrazine to show that the molecular formula for hydrazine is N2H4. So we can form a general expression for what hydrazine is, being NXHY, because we don't know how much nitrogen and hydrogen is in this formula. We know that it reacts with oxygen because it's a combustion, and we are forming nitrogen dioxide gas, and we're forming water vapor. It also tells us we're reacting with oxygen in the question as well. So given this, we can form that equation. We don't know what the coefficients are, and they've been represented with question marks here. Since pressure and temperature are constant, since we know that the temperature is 400 degrees Celsius and pressure hasn't been specified, so we can assume it's constant, the volume is proportional to moles. And so therefore, because we produce 2 liters of nitrogen, 2 liters of water vapor, and 3 liters of oxygen, this tells us the molar ratio between these 3 parts in a 3:2:2 ratio. And finally, all that's left is to balance out the nitrogen and hydrogen to solve for how many there should be. So given that there are 2 nitrogens over here and that there are 4 hydrogens over here, it tells us that X should be equal to 2, Y should be equal to 4, and hydrazine is N2H4. If you've seen this before in your studies, this shouldn't have been too difficult of a solve. This is more venturing into like a year 11 mod 2 sort of question. Then part B asks for the relationship between the acid equilibrium constant Ka and the corresponding conjugate base equilibrium constant Kb, being shown as Ka times Kb equals Kw. Use a relevant equation to calculate the pH of a 0.2 mole per liter solution of N2H5+ using the following data. The Kb of hydrazine is 1.7 times 10 to the negative 6, and the N2H5+ is the conjugate acid of N2H4. Okay, so what we can do is, because we know that N2H5, the acid, we have 0.2 moles of it. We know that if we were to react with water, we can create a Ka expression. So we can react N2H5 with water. So if we were to show this as a reaction, we'd have the following signs. And this gives us N2H4 and H3O+ as our products. The initial concentration is 0.2 mole per liter of N2H5+, 0 of N2H4, and 0 of H3O+. Because water is a liquid, it means we can leave it out of our calculation. So if we include states as well, I'm going to change the color to be a little bit clearer. Sorry, AQ. Rather than AQ, sorry, gas. Hang on, not gas. It's a solution, sorry, AQ. Everything is now AQ. Cool. And that means for H2O, we don't worry about it. We can cross it out. And the changes are all in terms of X in a 1:1:1 ratio. We can form our Ka expression from this equation. And we can also say that Ka is equal to Kw on Kb, rearranging this expression from before. Now, we can then say that Kw on Kb, which is what Ka was, is equal to the same thing in this expression, subbing in the x's, x squared, and 0.2 minus x. It would be better to have this with obviously shown as follows to avoid confusion with the brackets. Now you can apply small change assumption and also substitute in your Ka value, Kb value and Kw value. So Kw is from your data sheet, KB given in the question, and small change assumption means you cross out this x. Since it's so small compared to the 0.2, you may as well not count it. And the reason why you can do that is because the Ka and Kb are both going to be considerably small. Ka is going to be even smaller than this, something probably like 10 to the negative 8, given that Ka times Kb equals Kw. And we can assume that therefore the x formed is very, very small. Solving now, we can solve for x, which gives us hydronium concentration. Plug that into your pH. That gives you your 4.46, which is your pH, to 2 decimal places, given that we have 2 decimal places used, 2 sig figs rather, used here. We also, actually no, that's all we use. We use 2 sig figs here, and we have the Kw from your data sheet, which is also given to 2 sig figs, I believe. So your ending answer with the pH is left to 2 decimal places with a special rule. For pH, leave to decimal places, but leave to the least sig figs in the question, or the least decimal place in the question for the log-based units such as pH, pKa, pKb, etc. So, question 32, arguably the trickiest question in the paper, in my opinion. It's 5 marks, and it's quite an innocuous looking question from the STEM. It says the following 3 solids were added together in 1 liter of water. So you have magnesium nitrate, sodium hydroxide, and sodium carbonate of varying mole amounts. Which precipitate, if any, will form? Justify your answer with appropriate calculations. So, when added together, you can first of all start by saying all 3 of these will fully dissociate in solution to give their relative mole concentrations. Because you have 1 liter, you will have 0.06 mole per liter of magnesium, you will have 0.002 mole per liter of carbonate, you will have 0.012 mole per liter of nitrate, which is twice of 0.006 given the 1 to 2 ratio. You have 0.01 plus 2 times 0.002 mole per liter of sodium, and you have 0.01 mole per liter of hydroxide. And with the nitrate and sodium, these are just spectators, so they're actually not going to be very important for the question. You didn't have to calculate these, but we've just done it for completeness. Now, the first thing you have to think about is what's happening in the situation. You've placed all of these ions in solution, and the question is, what will precipitate? We know that typically the substance that will precipitate first is the one that is the least soluble. So the one that is least soluble is correlated with a substance that has the smallest KSP. And this will precipitate first. Okay. So, when added together, out of these, the possible precipitates we can form, to consider our options, we can possibly make magnesium hydroxide. We can possibly make magnesium carbonate. And everything else will be soluble. Magnesium nitrate, magnesium nitrate will be soluble. Sodium nitrate, sodium anything will be soluble. And so it's basically just out of these 2. To figure out what's going to precipitate first, we jump over to our data sheet and we compare magnesium carbonate with magnesium hydroxide. And we see that magnesium hydroxide is smaller in its KSP and will precipitate first. So we must first figure out how much magnesium hydrate can precipitate, if at all. So that's where our working starts. We then go on and say, magnesium hydroxide will precipitate out first because it has a smaller KSP compared to magnesium carbonate. Now this is just what we said. Q is equal to magnesium times by hydroxide squared, since there'll be a 1 to 2 ratio in the dissociation. You can sub in your values for magnesium and hydroxide concentration because nothing's precipitated yet, and you find that it is 6 times 10 to the negative 7, which is greater than the KSP of 5.61 times 10 to the negative 12. Therefore, you will precipitate magnesium hydroxide out. That's the straightforward part. The difficult part is then looking to see what happens beyond this point. So There's a few things you have to consider. The reasoning is as follows. So hydroxide is going to act as the limiting reagent for precipitation with magnesium. And I'll explain why this is the case. This will all fully precipitate the magnesium and hydroxide before you precipitate any magnesium carbonate. So you have to account for all the magnesium hydroxide coming out of solution first before you then look at the magnesium carbonate solubility and whether that has QSP that's greater than KSP. Now, what we initially thought and we realized was wrong was that if you considered the initial point in time where you had all of the magnesium hydroxide and carbonate concentration at once, if you reach saturation for, if you reach the solubility concentration for magnesium hydroxide, you would still have plenty to reach that of magnesium carbonate if you then calculated it straight away. However, this is wrong because even if you were to form magnesium carbonate instantaneously, if magnesium hydroxide is less soluble, that will continue to precipitate out, which removes hydroxide from solution and continues to shift, removes magnesium from solution, continuing to shift the equilibrium towards dissolving any form magnesium carbonate unless there is sufficient magnesium to supply both precipitates. And the idea is you will always have to factor in magnesium hydroxide precipitating fully first. So what we must do is find how much magnesium hydroxide precipitates. And since the hydroxide is deemed limiting in the following step, where we find magnesium concentration, hydroxide concentration, we already know this from the start, and we compare them in the ratio of 2 to 1, we find that the hydroxide is a limiting reagent. And going on, we can say that because the KSP of magnesium hydroxide is so small, we can assume that the amount that stays in the solution is virtually negligible. So the KSP being so small means that a very, very, very small amount dissolves in solution. So it might be like, say, 0.000000001, hypothetical number, but compared to 0.01 or compared to 0.006, it's super small that you may as well leave it out. So that means that we assume that the moles of magnesium hydroxide form is 0.01 moles per liter. The magnesium concentration after precipitation is 0.006 minus 0.01 on 2 to factor all of the magnesium that got precipitated out, and that leaves you with 0.001 mole per liter of magnesium in solution. And when you plug that in to try and test it with the remaining carbonate in solution, which hasn't precipitated at all yet, you end up with 2 times 10 to the negative 6 as your QSP, which is in fact less than 6.82 times 10 to the negative 6, telling you that no magnesium carbonate precipitate forms. It's a tricky one. It's really tricky, and it is very easy to take an easier route without thinking a bit more deeply about the intricacy of what precipitates first, whether it should go to completion or not. And initially, we actually got this wrong. So having a think back, getting some feedback, we were able to then patch it up. This makes a lot more sense, and we believe this is going to be the answer for question 32. All right, question 33, 7 marks, and it is your archetypal back titration. Chalk is predominantly calcium carbonate. Different brands of chalk vary in their calcium carbonate composition. The table shows the composition of 3 different brands of chalk. We have brand X, Y, and Z, all with their relevant percentage compositions. The following procedure was used to determine the calcium carbonate composition of a chalk sample. Sample of chalk was crushed in a mortar and pestle. 3-gram sample of crushed chalk was placed in a conical flask. 100 mils of 0.55 mole per liter HCl was added to the sample and left to react completely, resulting in a clear solution. Okay, so essentially what's happened is we've now taken this chalk, 3 grams of it, and we have completely reacted all of the calcium carbonate with this HCl in excess, and there is now an excess amount of HCl left in your mortar and pestle. So there's some HCl excess left. Results of the titration are recorded, and these are done with 0.1 mole per liter of KOH. Trial 1, 2, 3, and 4, you have the total used, and of course you have your, again, archetypal rough titration. Get rid of that, cross it out straight away. Question is to determine the brand of chalk sample, include a relevant chemical equation in your answer. For 7 marks, it's actually quite straightforward what you have to do here. So starting out, all you need to do in a back titration is work from back to front. That is your thought process. So write out your equation for the last reaction that occurred, and we're going to start with our average titer, finding that out too. So we have our equation, HCl reacts with KOH to make KCl and H2O, states are shown. The average titer of KOH is the average of the 3, so of course there should be brackets here. The formatting doesn't really show it too clearly. And 7.15 mils is the average. Cool. This means we can find the moles of KOH that is used to neutralize the excess HCl, performing 0.1, which is the concentration of KOH, times by the average titer volume, giving you 0.000715 moles. Now, the moles of HCl is equal to the moles of KOH, and this is the moles of HCl that were excess after the large amount was added and reacted with the calcium carbonate. And so that's equal to 0.000715 moles in excess, since it's 1 to 1. The initial HCl the initial HCl moles can be found now by looking back to the 100 mils of 0.55 mole per liter of HCl and accounting for how many moles total were used. So 0.55 times 0.1 gives you 0.0055 mole. And the reacted HCl, which is of course what you want because this reacted with your carbonate, which we'll see in a second. We can find how much reacted by taking the initial and taking away the excess number of moles. And we can find the excess moles by multiplying by, yes, the aliquot factor. So we're taking a 20 mil aliquot, which means we're taking 1/5 of how much was reacted. So we have to revert that, which is why we do 0.1 and 0.02. That gets us back to the true amount of moles of HCl excess in the original 100 mil solution. And that would end up giving you a reacted HCl mole amount of 0.051425. That's the first phase of this back titration done, and we're in the home stretch. So we now know, we will know in a second, the equation for calcium carbonate reacting with HCl gives you CO2, H2O, and CaCl2. Again, you can show states if you wanted to, so solid, aqueous, and you probably should show states, liquid, and aqueous. The moles of CaCO2 to HCl is shown as 1 to 2, as they react in a 1 to 2 ratio. Thus, the moles of calcium carbonate is equal to half the moles of hydrochloric acid reacted, and it should be half of this number. Thus, the mass of calcium carbonate is equal to moles times molar mass. We can multiply out by the molar mass of calcium carbonate, 40.08 plus 12.01 for the oxygen, 12.01 for carbon, 3 times 16 for the oxygen, which gives you 2.5736 grams of calcium carbonate. And the percent mass, all that's left to do is divide by the original tablet mass of 3 grams, multiplied by 100%, which gives you 85.785%. And we should also factor for the sig figs we should be leaving to. We had 3 sig figs all used here. We do have 20 mil aliquots. Just checking, is that used? Technically, we don't have to use it. Oh no, but then we have 0.1. It's going to be 2. Should be 2 sig figs. So technically, our answer should be left to 86%, but because we're just matching it up to one of these values, it's going to be closest to X. But we want to always consider our sig figs anyway. So that is all to be said about question 33. Question 34, 5 marks. A 0.01 litre aliquot of an acid was titrated with 0.1 mole per litre of sodium hydroxide, resulting in the following titration curve. It is one equivalence point signifying it is a monoprotic acid, and it also has this initial sharp rise signifying this is likely a weak acid as well. So they ask us to calculate the Ka for the acid used, and the method that we take uses the equivalence point and it uses the initial starting pH. So we know it's monoprotic acid because it's one equivalence point, as we said. Then we can say that the starting H plus concentration is 10 to the negative 2.5 mole per liter, taking the pH and putting it as the negative power. And we also know, since HA dissociates to form H plus and A minus in a 1-to-1 ratio, that the A minus concentration should be equal to the H plus concentration, which is equal to 10 to the negative 2.5. That is our first step. Then we can also figure out how much HA undissociated total there was. You can also say this is the total H plus amount, like the total, by looking at the moles of sodium hydroxide used to neutralize it in its entirety. So we can use the concentration, 0.1 mole per liter, multiplied by the volume, 0.024 liter, and that comes to a mole amount of 2.4 times 10 to the negative 3 moles at equivalence point. Cool. Taking the volume of acid initially, 0.01, we can find the concentration, therefore, by dividing through by that, and we get 0.24 moles per liter of HA undissociated initially before it ionizes into H plus and A minus. The Ka can then be found by taking the H plus concentration, the A minus concentration, and dividing by the HA after ionization occurs. So H plus and A minus are both substituted in the top, and the HA after ionization is 0.24. Take away how much turned into H plus and A minus, which is 10 to the negative 2.5, and this will then give you an answer finally of 4.2 times 10 to the negative 5 to 2 sig figs. An alternate method some people may have used is justifying a small change assumption and saying that this wasn't that significant. You could justify it by saying that the concentration of H plus relative to the to the concentration of HA is relatively small. It's like about 1.3%, and this would be less than 5%. You're going to make a small change assumption. I would just calculate it out because it's not that rigorous. It's just an extra step. And actually, in truth, for this question, it doesn't matter. The answer ends up the same when you express it to 2 sig figs. I think it's 4.22 in this case if you don't do the small change assumption. And if you do the assumption, it's 4.17. They both round up, or round to 4.2 times 10 to the negative 5. So that's 34 part A. Part B then asks about the concentration of NaOH, which is 0.1 mole per liter, and you're asked to explain why the pH of the final solution never reached 13. So to reach a pH of 13, you need to have a pOH of 1, which requires a hydroxide concentration of 10 to the negative 1 or 0.1, not 0.01. 0.1. Cool. So the solution can never reach pH 13 because you're already adding in 0.1 mole per liter NaOH. This is pH 13, but you're adding it into a solution that already has other volume. It already has more acidic substances that were once neutralized, and so you're going to approach 13 indefinitely, but you will never, ever, ever be able to reach that pH of 13 because you are not adding a concentration that is higher than 0.1 mole per liter of sodium hydroxide. Okay, cool. So that's 34. 35, 5 marks. A purple solution at 25 degrees Celsius contains a mixture of two different cobalt complexes which are at equilibrium. COCl4, H2O, COH2O6, Cl-. Another case study. So this is NASA really signaling to us in the coming years we should really nail down our case studies, get them really solidified because they're thick. They're really coming thick in this exam. The results of heating and cooling of a sample of this solution are given in the table. You see that it turns blue at 80 degrees Celsius and it is pink at 0 degrees Celsius. The energy profile is shown where you have essentially not endo and exothermic profile going from a higher a higher enthalpy level to a lower enthalpy level, and your enthalpy change, your delta H, is therefore less than 0 exo. Question is, how do collision theory and LCP account for the color change to pink when the solution is cooled? Refer to the energy profile diagram in your answer. So they've been kind enough to actually invite you in to talk about both collision theory and LCP in this exam. Very kind of them to give you this many marks on these relatively straightforward Mod 5 concepts. And a model response is shown below. So from the energy profile diagram, it's clear that the forward reaction is exothermic and thus the reverse reaction is endothermic. Probably a mark just for saying that. The LCP justification. So when temperature is decreased to 0 degrees Celsius, the system will favor the forward exothermic reaction to put heat back into the system and thus partially counteract the change in accordance with LCP. If this was the first time in the exam, you'd define it. To be safe, you can define it anyway. But here, we don't need to. I'd probably just slot in here in accordance with LCP. Therefore, this will favor the production of products and thus COH2O6, 2+, turning the system pink because we're making more of this product. Collision theory. Different justification. Has to talk about rates, has to talk about the comparison of forward versus reverse rate. So when temperature decreases, both forward and reverse rates decrease as there are fewer successful collisions and a lower proportion of collisions with kinetic energy greater than activation energy. So you acknowledge that it affects both forward and reverse rate. However, the reverse endothermic reaction will decrease by more because it has the higher activation energy as shown in the diagram, and thus experiences the bigger proportional change. These are the key words that we drill in. Proportional change is the reason why you then favor one side, particularly the side that has the greater activation energy, so the endothermic side. Therefore, the forward rate exceeds the reverse rate, and this results in a right shift until equilibrium, which favors production of products and thus the pink COH2O6 2+. You're justifying the exact same thing through two different ways and referring to the energy profile diagram. The mark allocation is pretty clear. Question 36. This question was predicted in Catalyst's exam predictions for 2025. It was in Mock 1 and Mock 2 in a similar format, and anyone who's seen this before could have pretty much nailed this question type. The question reads, use the data sheet provided in the information in the table to answer this question. You have the proton NMR data. The relevant different functional groups are shown with their shift. And in the exam, students were told to add on an extra row for carboxylic acid as shown. So I've gone and done that. Consider the molecule shown, which is a propanoic acid. For each of the following instrumental techniques, predict the expected features of the spectra produced, refer to the structural features of the molecule in your answer, and you're asked to talk about all of the organic spectra. IR, carbon, proton, mass, everything. Okay. So, starting off with IR, you can start by saying there's a very broad peak. There would be a very broad peak from 2,500 to 3,000, which represents the OH group in the acid. You would then also expect a narrow peak from 1680 to 1750 for the carbonyl. And if you want it to be extra good, even though it's in the fingerprint region, you can say you may expect something in the 1,000 to 1,003 for the C single bond O. But again, it's in the fingerprint region, so you didn't really have to say it. And they said ignore C to C, C to H. Cool, that's IR done. Then carbon NMR. There should be 3 distinct carbon environments as labeled here, 1, 2, 3. There's no symmetry in this molecule from what we can tell. So based on this, signal 1 should be shifted to 160 to 185 because of the deshielding effect of the carboxylic acid. So it's the most downfield. We should then expect for signal 2 as labeled that it's less downshifted because it's a little bit further from the electronegative oxygens, but closer than carbon 3. And so finally, signal 3 should have the least deshielding effect, and both of these should fall within the range of looking at our data sheet, within the range of 20 to 50 for the carbon attached to the carbonyl carbon, and then 5 to 40 for the one just attached, single bonded to a carbon with no carbonyl attached. So that's what we'd expect there for this. Moving on, we have our proton NMR, a lot more to break down here. We expect 3 signals corresponding to 3 unique H environments. I'll just keep the screen. Actually, I'll change the display. Let's do this. Okay, cool. So we have 3 hydrogen environments, 1, and then this is 1, and then this is 1. Environment A has you can talk about several things in HNMR. You want to talk about your splitting, you want to talk about your integration, you want to talk about your chemical shift. All those things should be addressed for a complete, comprehensive response that doesn't miss anything. So, for environment A, there should be an integration of 3, since there are 3 hydrogens in the environment. It should be a triplet, since there are 2 neighboring hydrogens, 1, 2, and by the n+1 rule, there should be 3. It's the least downshifted because it's furthest away from the electronegative oxygens. And looking quickly at what we expect the shift to be, I would reference the data and say that because it's a CH3 attached to it's a CH3 attached to a CH2. I mean, yeah, it's just a CH3. So it's going to be somewhere in the 0.7 to 2.1 range, and I'd actually reference that in my data, since it's a CH3. Cool. Environment B, integration of 2, since there are 2 hydrogens in that environment, so the ratio 3 to 2 makes sense. Quartet, since there are 3 hydrogens on neighboring carbon environments, plus 1 is 4, that gives a quartet. And again, more downshifted due to closer proximity to electronegative oxygen, and we can have a look at what that might look like. It should be in this box, since we have the CH2 CO, which is corresponding to the carb acid carbonyl. Cool. And then the final environment should be a singlet. So H should be a singlet with an integration area of 1. It's a labile proton, so only a singlet. And we can discuss the shift in terms of that extra row. It should be 9 to 13. We should state that, and we should say it's because of this COOH. And that rounds out our H&MR discussion. Talk about all the environments, what you expect to see for each of them. There's a lot of marks we picked up there for sure. Finally, what you expect to see on your mass spec. So with mass spec, you'd expect to see your molecular ion peak reflecting the molar mass, 74. You can calculate that and make that judgment. You can also talk about potential peaks that you might see for smaller fragments. So mentioning that CH3 might show 15, 29 might show for C2H5, we might get 45 for COOH as prominent fragments. That would definitely bolster your mass spec, portion of this response. And I would think that for the 7-mark allocation, when they're doing the impression-based marking, if you talk about fragments, it really just lifts your response up above the rest. So I would highly, highly encourage to not just mention the molecular ion, yes, it's important, but also to mention all the potential fragment sort of mass per charge that are very, very abundant. And that would be all that's needed for this question. As I said, this was littered through our exam intensive. It was in our exam predictions. We saw this coming. It's never really been asked before, but it's just waiting to be asked. And here it came. So very happy with this one. 36, 7 marks. That was all you needed. Okay, and finally, question 37. It's a reaction pathways question, actually pretty straightforward, to be honest, as a final question of the HSC. 4 marks. Compound A has the molecular formula C5H10. We're thinking immediately it's an alkene, given it's in a CnH2n formula. The information below shows some chemical reactions beginning with this compound. Compound A reacts with H plus and H2O to form B and C. So this is a hydration reaction. We're making alcohols, B and C. Compound B does not react with H plus and Cr2O7 2 minus. So it's telling us maybe we have a tertiary alcohol on our hands with compound B. Compound C reacts with H plus Cr2O7 2 minus to produce compound D, and compound D does not react with sodium carbonate, which tells us compound D is not a carboxylic acid, is not reacting with carbonate, fails that test, and compound D has to be a ketone. So we're told that compound B as a result, compound C as a result of that is a secondary alcohol, compound B is a tertiary, D is a ketone, and A is our alkene from the very beginning. And it likely has a methyl group on it somewhere in order to make it a tertiary alcohol. So looking through, finding each of these compounds, it's really not too bad. We can find compound B first, because we know it's a tertiary alcohol with 5 carbons. It has to be this butanol, but it has a methyl on where the hydroxyl is, and it's on the second carbon. Understanding then C has to be formed from the same alkene. It's either going to be the alcohol on the carbon to the left or the carbon to the right, but because we know it's going to be a ketone that forms from its oxidation, we know this hydroxyl is going to be on the carbon to the right. And finally, the ketone that forms from the oxidation of C is going to be this here, replaces the OH with a carbonyl, and finally we can go back all the way to A and say that's where the double bond is between carbon 2 and 3, and we can go back and name all of these as well, going all the way back to the start. 4 marks, I think it's good to just show all these compounds, name them out anyway. You probably wouldn't need to name them for marks, but we've done so for completeness, and that's probably one of the kindest final questions in the HSC for some time. So that's a wrap for the 2025 HSC Chemistry exam. It was an easy one. I think the Band 6 cutoff is going to be 89, 90, right around that range, and the scaling is not going to be significant up towards 80 plus. You might get 1 or 2 marks in above your raw mark because of how relatively straightforward this exam was. Can I say that I'm pleased with the exam? No, I'm actually quite disappointed. I was hoping for a hard paper this year, given that we've had 2023 and 2024 easy papers. It looks like they've just decided that HSC Chem is going to be an easy subject from now on. I hope that we return to the ways of 2020 to 2022 in the 2026 paper, but that's pretty much all I have to say. If you've just graduated and you've just finished HSC Chem, this may be your last exam. Congratulations, please celebrate, enjoy yourselves, take a good break from studying, and all the best, genuinely, for your life beyond HSC, because you've all got exciting futures ahead, and I'm so glad to have been, at least a small part of your journey to getting to the top of this massive, massive HSC mountain. So thank you very much for tuning in, and if you're actually not one of the class of 2025 just graduating, and you're class of 2026 or later, Catalyst program is actually open for term 1. We're accepting enrollments, and we're running a special secret promotion. If you've gone to this point, we are accepting enrollments for term 1, and if you enroll for term 1, you get access to the rest of term 4. So if you're preparing for a Mod 5 exam, Mod 7 exam this term, you can join us for term 1 and get access to all of the Mod 5 and Mod 7 stuff. So submit a form through our website. Just click the Enroll Now button and submit a quick form. One of our team will give you a call to run you through all the details, answer any questions you have, and make sure if it's actually a right fit for you, because if it's not, we'll tell you, and it's important that what you're going into is you fully understand how it works, whether it will work for you or not, and for most cases it will, but we will be honest if we don't think it'll be a fit for you. So submit a form, see if we can help you achieve your dream marks, whether it's a Band 6, high range Band 5, 99 plus ATAR, literally we don't care, but we will help you achieve your absolute full potential in the next year or 2 years. So that's all from me. It's been a pleasure, again, presenting the 2025 HSC exam for you guys. If you have any questions, drop them in the comments down below. Subscribe, like, everything, do all that. And I'll see you back in the next video. Thanks very much.